Okay, so this is the final lecture of ECE641 Model-Based Imaging, the Pandemic Edition. So I don't have a mask on because I'm at home by myself. Actually, my wife is in the house too, but that doesn't count. She's part of the same pod, as they say. So let's see. So today I want to cover Markov random fields, the general case of Markov random fields, which I was a little bit inspired to do that yesterday because I was on a committee of a Professor Keck's student who did a very nice job in bug location in software using semantic models. And he was using Markov random fields. So I was like, wow, you know, that's nice. So I feel like I should cover it. And it also is a pretty major theme for the class. So it's nice to cover a little bit more, cover it in a little more generality. So let me hit on some of that. Let's see. So let me see. I need to share the screen. I need to share the dot cam, I think is what I really need to share. Okay, now this, as usual, for some reason, this doesn't focus. Let's see. Oh, there we go. Okay, so now it kind of looks out of focus, but it's really not. It's the what's out of focus is it's the projection of the light. So it makes it, and it creates an illusion of it being out of focus. Okay, hold on. Let me get that. There we go. Okay, now. So, see, this is 96, right? Okay. What happened to the 97? Oh, yeah. Okay. So, okay. So, Markov random field. So the idea of a Markov random field, and oh, why is this not staying in focus? Oh, thanks. That's very bizarre. I don't quite get it. Maybe I'm not giving it enough time to settle down. Oh yeah, it's continuing the hunt is the problem. Let's try that. I never did this before. Hold on. Huh, that's funny. Let me try it again. Huh, I have no idea why I was doing that. Anyway, okay, Markov random fields, discrete. So we have X, S, okay, for S, a member of some larger set S. So this is a set of lattice points. Okay, and then XS is going to be a member of a discrete set. So it's a member of a set without loss of generality, 0 through m minus 1. So there are m possible states to each point. And then this thing denotes a subset of S, not a member, okay? Because S is a set, okay? It's the neighbors. And there's a couple properties in the neighborhood. That S is not a member of partial S, okay, for all S. And for all S and R, if S is a member of, say, partial R, then it must be that R is a member of partial S, okay? So neighborhood, there's a symmetry relationship to neighbor being neighbors. If I'm your neighbor, you must be my neighbor, okay? So, okay, fine. Now, what happens then is that a Markov random field, so the defining property is that the probability distribution, I'm going to use a little bit sloppy notation here in order to make it a little simpler. I'll just put here XS, okay? That means the probability distribution of XS. I'm doing exactly what I told you not to do at the beginning of the semester, which is I'm using the dummy variable to denote the dependency on the function, but we all know what I mean, okay? And that, and then this is given, you know, XR for R not equal to S. So this is the rest of the image. Is really only dependent on XS given X partial S. So this is conditionally independent given neighbors. Okay, so the idea is that you have an image. This is a pixel. You got a neighborhood like this. Okay, and the neighborhood, the idea is that if you know the neighbors, that pixel XS, this is XS, that neighborhood, this is X partial S, okay? So it's this XS is conditionally independent of this stuff out here, given the neighbors, okay? So that's not an unreasonable assumption. It's a little bit like the AR assumption, and we talked about that a lot in the Gaussian case. But now we're talking about discrete Markov random fields. So they're totally not Gaussian at all, okay? All right, now, okay, so that's the defining property of a Markov random field. That there's sort of a local dependency in the model, that the conditionally, that there's no point in trying to predict this pixel with any more than just the neighbors, because beyond that, it doesn't give you any more useful information for predicting the pixel XS, okay? All right, so now here's the thing that's kind of interesting. So we have a concept of clicks. Okay, so we have clicks. And I talked about clicks before, but a click is, so you have a set, C, it's a subset of S, so it's a subset of pixels. Okay, and for all S and R members of C, we have that R is a neighbor of S. Okay. Okay. Or R equals S. Okay, but that's sort of, or I can say for all R not equal to S, then this has to be true. So, example. So I can have an example is so I have a 4-point neighborhood, or I say 8-point neighborhood. So basically, clicks are a function of the neighborhood. So you have to have a neighborhood with a particular neighborhood, then you can determine what the clicks are. So you know what an 8-point neighborhood is. It means that, you know, it's like this. Let's see. So so this is the point in question. These are the neighbors. So those are the neighbors of that point, right? call it an 8-point neighborhood because there's 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what are the cliques? Cliques. So it's every pair that, if you have a pair of pixels like this, that's a clique because they're neighbors of each other, right? If you have a pair like that, it's a clique, right? If you have a pair like this, it's a clique, okay? If you have a pair like this, it's a clique because they're neighbors of each other, okay? Now, also, just a single point by itself is a clique, okay? Right? And now, okay, now what about, you also have, if I have 3 points, that's a clique, right? And that's a clique, okay? And that's a clique, okay? And that's a clique, okay? So those are 4 different cliques. And then also this is a clique. Because see, if you look at it, every pair of pixels in that group of 4 pixels is a neighbor of each other, okay? So that's a clique. Okay, so why do I care about cliques? I care about cliques because I'm going to define a thing called a Gibbs distribution, okay? So Gibbs distribution. So Gibbs distribution. So I can have a function. So first of all, I'll call that set of, excuse me, all cliques. Okay. Now the set of cliques are, well, actually, I don't necessarily have to give the word. It's the set of cliques, okay? I don't necessarily have to have all cliques, but let's say I do have all cliques, okay? Okay, it might be all cliques, it might not all be, but here we'll assume it's all cliques, okay? So now what will happen if I have a C is a member of this C? Okay, now, a set of cliques, a clique is a set of pixels. So a set of cliques is a set of sets of pixels, right? So it's a little bit abstract, right? Okay, but you need to keep track of that. So this is a set of sets of pixels, right? And for every clique, okay, then I'm going to have a function v of c, okay, is, v of c is x of c, okay? And x of c is equal to, it's like the set of pixels xi such that I is a member of C, right? So this is the value of x at all the pixels in the set C, okay? So, and this is some function. I have to subscript it by C because it depends on the particular clique. It's a different function for each clique, right? Fine. By the way, this is discrete. In other words, if let's say M is 2, so there's 2 possible states, and the clique contains 3 pixels, then there are 2 to the 3, which is 8 different states that this thing can take on. Okay, it's discrete. Now, I'm also going to define, so this thing here is called the potential function. And then we define a thing called the energy function. And the energy function u of x, so this is the whole enchilada, as they would say. This is the complete image, okay? And it's going to be formed by, it's a function, so the energy is a function of the complete image, and it's going to be equal to the sum over all the clicks. So this is a member of the set of clicks of some function c of x of c. Okay, and that's the energy function. Are you confused yet, by the way? It's not really that complicated. It just means that we have an image, right? We take now the image, we break the image is formed of pixels. The pixels, we can form subsets of pixels, which we call clicks. So for each click, we can have some function of that click. Okay, and then we sum that over all the clicks. And then that's the energy function. And then a thing called the Gibbs distribution. That's P of x is equal to e to the minus u of x. Now that's not a legitimate probability distribution because it may not sum to 1. So I have to divide by something, 1 over z, okay? It normalizes it. So it's, and this is called the Gibbs distribution. In thermodynamics, for some reason they call the terms Gibbs distribution and Boltzmann distribution are pretty much interchangeable. In the mathematics community, for some reason, they tend to call it Gibbs distribution more often. And in the physics community, they tend to call it Boltzmann distribution more often. But as far as I know, there's no distinction between the definitions, okay? And I don't know why that has 2 different names, but it appears to have it. But anyway, so this is the Gibbs or Boltzmann distribution. And okay, fine. So now, here is the interesting thing, okay? Okay, theorem. And the theorem has a name. It's called Hammersley-Clifford. Which is particularly interesting because Hammersley and Clifford never wrote a paper about it or even published anything as far as I know about it. It was actually published by somebody else, and then the person attributed it to them. So like, I guess they, over coffee or whatever, Hammersley and Clifford explained the proof, and then this other guy actually wrote the proof down and published it. But Hammersley and Clifford, but they actually, it's one of the rare times, you know, well, assuming that Hammersley and Clifford's idea really was theirs, that people got credit for something without publishing it. Okay, so, but the guy who actually published it was a guy named Baseg. And anyway, so, okay, so here's the big idea. The big idea is this, I actually have a graphic in here. Let me see, this is 298. This is 299. Okay, right. 300. Okay, so the idea is that if X is a Markov random field with distribution P of X, okay, and which is greater than 0. So that's really the constraint, that the probability distribution has to be greater than 0. Okay, so in other words, for all states of the entire X, the probability has to be greater than 0, which isn't, in a practical sense, a very strong assumption, right? Because you can always make some of the states very improbable, but not 0 probability. That if it's a Markov random field, then it has to be possible that you can write it as P of X is a Gibbs distribution. Okay, so this is an if and only if condition. So why is this important? It's important because if you have a Markov chain, I mean, okay, it's often, I mean, as we've spoken about before, random variables x and distributions p of x are not the same thing. So p of x is a deterministic. This is a random variable. Just because a particular random variable defines a particular distribution, but that distribution doesn't define a particular random variable, because you can have many random variables that have the same distribution. You can have an infinite number of random variables that have the same distribution, okay? But knowing something about if this is a, so if we say that this x is a Markov chain, then we know the Markov chain distribution can be written down as, if it's a homogeneous Markov chain, we know that the Markov chain probability distribution can be written down as the product of all the transition probabilities. But if this is a Markov random field, okay, so we know that that pixel is dependent upon its neighbors. But how do we write down parametrically the distribution of this Markov random field? You might be tempted to say, well, look, what I'll do is I'll say, well, okay, if it was a Markov chain, I'd say P of S of XS given X its neighbors, right? If I take that and I say, okay, well, that's the conditional distribution of this X given all its neighbors. And what I could do is take the product over S, right, a member of S. And then the question is that equal to the probability distribution of the complete Markov of the entire thing, of the entire Markov random field? And the answer is very definitely no, not true. That is not true. Okay, so people would, that is true for a Markov chain because you have a causal relationship. In a Markov chain, if you have a bunch of states, they go like this, then you can calculate the probability of the sequence by taking the probability of the first event, and then the second event conditioned on the past, and then times the third event conditioned on the past, times the probability of the fourth event conditioned on the past. You can just multiply them together and you get the right answer. But that doesn't work in 2D for a Markov random field because this is loopy. And loopy doesn't mean like goofy. It means that there are loops in the dependency. Well, maybe it means it's goofy too, but the problem is that the dependency is going both ways. So here what ends up happening is this pixel is dependent upon all the pixels. So it's going both ways. So you have loops in the dependencies. So it's called loopy. Or loops, because you can go around in loops like this, right? Here you can't go around in a loop because, yeah, I mean, there's no loop, right? So here there's a loop. You can go around in this loop. So the loopiness makes this untrue. So then the question is, well, if I can't write down the probability density function, how do I write it down? Well, the answer is I can write it down as a Gibbs distribution. Now, you get part of your cake, but you don't get the whole cake. You don't get the cake and eat it too, right? You don't get everything you want. You get some of it, okay? So it means that if X is a Markov random field, if and only if P of X is equal to 1 over Z times e to the minus U of X, okay? Where U of X has the functional form sum over C, a member of all clicks, of VC of XC. So you could parameterize this because if you go back to the clicks, okay, if you have a click with 4 pixels in it and say M is equal to 2, right? Then, if M is 2 and there are 4 pixels, then there's going to be 2 to the 4th possible combinations. 2 to the 4th is 16, right? So you have 16 different values for the function. So we'll call this the 4 click, right? So the associated, we'll say it's V4, okay, of X4, I don't know, okay? And this thing takes 16 different values, depending upon, X can take on 16 different values, so the function can only gets parameterized by 16 different values. So the beauty of this is that now you have a way of parameterizing the distribution of all Markov random fields on that discrete grid. Okay, and that sounds all fine and well and good, and it is good, but the problem is that you don't know this. You don't know Z. What is Z? Z is this normalizing constant. So you know the probability distribution up to a unknown multiplicative constant, okay? And that constant in thermodynamics is known as the partition function. So kind of interesting, okay? So this is the general form of the Markov random field that we've looked at in more particular cases earlier in the semester. Okay, so this is the Hammersley-Clifford theorem that I just wrote down. So if you have an X, then it must have, it's easy to show that if something's a Gibbs distribution, it's relatively easy to show that X must be a Markov random field. The other direction is pretty tricky, actually. Okay, the proof is pretty tricky. That if X is a Markov random field, then it must have a distribution which is a Gibbs distribution. This direction is what's called constructive. So it's easy enough to actually find the conditional probability of a pixel given its neighbors if you assume that the thing's a Gibbs distribution. And we'll use that when we do calculations. The other direction is not constructive. You prove that the thing must exist, but it's really not a constructive proof. So what ends up happening is that it's kind of difficult to, if someone gives you a Markov random field, so in other words, if I give you a Markov random field, if they actually provide you with the conditional distribution, it's like the transition probability for a Markov chain. If they provide you with the distribution x of s given x partial s, if they give you this, it's hard to calculate the function u of x. This is, in principle, if you know this, you can calculate that. But this is difficult. Is difficult. On the other hand, going in the other direction, if someone gives you a u of x, that's easy. So it's easy to calculate the conditional probability of a pixel given its neighbors if you have the potential function, if you have the Gibbs distribution. But the important thing is the Gibbs distribution gives you a parametric way of writing down the distribution of the Markov random field. Okay? All right. Now, okay. So I think what I want to do is, okay, I'll have a, obviously this is going to have to be a little compressed. So what I want to do, oh, the Ising model. There's a thing called an Ising model. It comes up in physics. It's pretty cool, okay? So the problem with, so the thing with the Ising models is this, that they, around the Second World War, they were trying to understand a lot of, there was a period around the Second World War in which there was massive progress in physics, right? You know, some of it maybe not for the kindest of reasons, but it did occur. There was like, you know, they basically invented around that period of the 30s, the 40s, and the 20s, 30s, and 40s, they basically discovered quantum mechanics, and Heisenberg's uncertainty theorem, and a lot of the nuclear physics that led to, you know, nuclear power, and of course, you know, nuclear weapons. But that was the Manhattan Project. But so they were trying to understand a lot of fundamental physical behaviors. And one of the things that's really interesting is if you have a magnetic material, so it has like pluses, it has like little poles, dipoles, and they can either be oriented positively or negatively, something like this. I mean, I'm drawing some particular configuration, something like that. But you know, you have, so the idea is that you have a magnetic dipole a molecule and it's polar, so it can be flipped this way plus or this way minus, okay, plus minus, right? And the energy is associated with the energy of its neighbors. So what happens is that you can set up, it's like a 4-point neighborhood, okay? So the idea is that the energy looks like this. So J is, so X here, XS, takes on values of 1 or minus 1. So 1 means it's pointed up. I guess that's up. It's a positive polarization of the magnetic field, and that means minus. Now, if two neighboring pixels have opposite polarity, then the energy goes up. If you've ever played with magnets, you know that the magnets like to be oriented in the same direction. So if you have two things like this, they're happy. But if you do it like that, they're not happy. You let go, it flips back like this. Or if you let go of this one, it'll flip like that. So in other words, they want to both be oriented the same. And that's the same thing if they're oriented this way or this way, it doesn't matter, okay? So they want to be oriented the same. So the energy goes up when you have them going in the opposite directions, okay? Yeah, okay, now, so the energy goes up. So basically, you take like XS, right? And you take times XR, so, oops, R. So S is supposed to be a neighbor of R, okay? And now if they're both in the same orientation, then they're both +1, say, okay? So then you have 1 times 1 is 1. Or if they're both -1s, you have -1 times -1 is 1. So if they're both in the same orientations, this is 1, okay? Now, if they're in the same orientation, the energy goes down. It doesn't go up, okay? Because they're happy when they're in the same orientation. And happiness means lower energy. Okay? So then you have to multiply by a minus to determine the energy. And of course, there's some scaling coefficient, you know, depending upon what your units are, ergs or whatever it may be, so that there's some function here, J. So that's the scaling coefficient. So that is associated with the overall energy. And of course, then what you have to do is you have to sum that over all the pixel pairs, and we're going to sum over clicks, which are 4-point neighbors. So we have SR are clicks. Okay, so you're summing over all neighboring pixel pairs in a 4-point neighborhood, okay, of this quantity, right? Now, so you define that as U of X, right? And then the probability, so now here's what's kind of interesting. So if you look at this here, where is it? So this is 136, this is 7, 8, hold on. Oh, so this is like a little pattern, right? And what you could have pluses and minuses. And it turns out, if you really think about it, that the sum of this thing, this sums the energy associated with all the pixels which have opposite neighboring polarity. So every time you have two pixels in a 4-point neighborhood with opposite neighboring polarity, that forms like, that can be represented as the boundary. So essentially, what this does is this quantity here measures the length of the boundary associated with the neighboring pixels of opposite polarity. So this energy function is proportional to the boundary length, okay, of neighboring pixels with opposite polarity, okay? So that's 310. Okay, now here's the thing that's kind of interesting. So you have that P of X is equal to 1 over Z e to the minus U of X, right? Okay, so this is a Gibbs distribution. Okay, but I'm sort of jumping ahead a little bit. Okay, so we're going to take this function U. Okay, now, interesting fact. If you make, if you define E, we'll say E. So this is E bar as being the expectation of U of X where x here is distributed as p of x. So we'll put a p here because we're as a function of that p, okay? And now we say, okay, so that's the average energy associated with some distribution of states, right? And then we take h bar is equal to the expected value of, excuse me, of, right, is of the minus the log of p of x times, oh yeah, no, that's it, minus the log of p of x, okay? So this is the entropy. Now in thermodynamics, one of the fundamental laws, the second law of thermodynamics says that every system, as its entropy goes up with time, okay? Or it can't, or at least it can't come down, right? It turns out that if you, okay, you know, if people talk about the energy crisis, or at least when I was young, they talked about the energy crisis. Now they talk about renewable energy, I guess. But let's say you talk about energy. So you say, well, we have an energy crisis. And you'd say, well, that's ridiculous. We don't have an energy crisis because over here we have a boat, okay? Okay, there's a boat. And you say, well, the problem with the boat is we don't have enough energy to drive the boat forward because it runs out of fuel. You go, that's silly, okay? And we got plenty of energy. What we're going to do is we'll have like an ice cube making machine here, okay? And it'll like take the water in a little pipe, go into the ice cube making machine, and then the ice cube making machine will shoot out ice cubes. So we'll fire them out of a cannon. Okay, and so we'll have little ice cubes fired out of the boat. Okay, so as long as, and then it uses the energy it extracts from the water in the form of ice cubes to push, that's supposed to be the propeller. To turn the propeller to drive the boat forward, okay? Perfectly fine, no problem at all. Why is there any problem? Conservation of energy, good to go. You take the water, you extract the heat from the ice cubes, you shoot the ice cubes out, and then you use the energy extracted from the ice cubes to turn the propeller, okay? But we all know that doesn't work, does it? Like, could you have an ice cube maker machine? The ice cube maker machine would use energy. You're like, what are you talking about? But it's perfectly good from the point of view of conservation of energy. So what's the problem? I know there's got to be at least one person in the classroom who can answer my question. What is the problem? Why is this physically impossible? Alejandro, I'm depending upon you.
Oh, the efficiency of the process.
Yeah, but I need a specific, a little precise thing. Why is that physically impossible? What law does that violate? What law of thermodynamics does that violate?
Oh, off the top of my head, I think it's the third, but I don't remember.
Okay, maybe it's the third too, but it's definitely the second because
Okay.
it's basically reducing entropy instead of increasing it. So there's three laws of thermodynamics, of which I know the first two. The third is like enthalpy or something, right? But the first is conservation of energy. Sure, so this doesn't violate conservation of energy, but the second one is that entropy goes up. Here, entropy is going down. See, if you have like a tub of water, right? I'll draw the water like this. Of course, it doesn't really have. And you put a little plastic thing with a tube in it that allows the water to go between here, okay? Like, what would stop? And you'd say, well, I say, oh, well, here's what I want to do. I want to talk to the water and tell the water, water, could you please cooperate with me? And could everybody in here, like everybody on the left-hand side of this this thing, give your energy to the people on the molecules on the right-hand side, okay? And then this thing will freeze, and that thing will stay liquid. It doesn't happen like that, right? If anything, if this thing starts cold and that starts hot, then if you wait time, the heat will go from the hot part to the cold one, right? Because entropy goes up, entropy does not go down. In other words, the disorder of the system increases with time, right? So by logically thinking, what ends up happening is when the system is in thermodynamic equilibrium, the system goes to its highest entropy state. So if I start with the molecules of air all in the corner of the room and I let go of them, the molecules of air will spread throughout the room uniformly, okay? And so it goes to the highest entropy state given the constraints of energy, right? Can't violate the first law. So here's the interesting thing. So if I solve for, maximize, or I maximize H of P, right, subject to the constraint that EP is equal to E0, right? That's a constraint optimization problem. I maximize the entropy subject to a constraint on the energy, okay? By the way, I can solve a constraint optimization problem because we know about Lagrange multipliers in this class because we spent a lot of time talking about it. So that's equivalent to, what do you say, I maximize H of P plus, I'm going to have to subtract. It's easier for me to do minimization. So let me do a minimization. So I minimize over P minus H of P plus lambda times E of P. And the result is going to be equal to, I call it P star. Let me write that down again. So I maximize the entropy subject to constraint on energy. So I minimize the negative entropy subject to a constraint on energy. So I minimize over P minus H of P plus lambda times epsilon of P. And when I do that, I get a P star. I get the distribution that maximizes the energy constraint, subject to constraint on the, and maximizes the entropy subject to a constraint on the energy, right? If you can go to infinite energy, usually what ends up, as the energy goes up, usually the number of available states increases, okay? And then you have the, you can actually have, you can have higher entropy, but you can't, in other words, if you let me add heat to a system, I can increase the entropy, okay? But if you give me a fixed amount of energy that I have to work with, then the question is, what distribution of states achieves the maximum entropy, right? So another way of putting this would be, I could do the maximum over P of H of P minus lambda epsilon bar of P. That's the other way of saying it, right? And then as this is the Lagrange multiplier, and depending upon what I pick lambda to be, I'll get solutions for different levels of energy, but it all represents an answer for a constrained optimization problem where the constraint is on the energy, okay? This is, you can think of this E as like cost. So you're trying to maximize something subject to a constraint on cost, okay? So, and then what's the answer? Well, the answer is P star is equal to 1 over Z times exponential of minus 1 over, well, okay, oh shoot, beta times U of X. This is related to the Lagrange multiplier. Actually, I think it is the Lagrange multiplier. if you work out the problem. And what normally happens is that beta is assumed to be 1 over KB times T, where this is what's called Boltzmann's constant. And you can look up Boltzmann's constant in a book. I think it's actually not a measured thing. It's a defined thing, because you define Boltzmann constant, and that implies what temperature means, okay? So if you have Boltzmann constant, if you're using Kelvin, degrees Kelvin, then Boltzmann constant has particular units, okay? So so the idea is that that this is equal to 1 over Z times exponential of minus 1 over KB T times U of X. So what does this mean? It means that as you increase it means that a system in thermodynamic equilibrium always has a distribution of states that's the Gibbs distribution, which is kind of interesting. And that's why the Gibbs or the Boltzmann distribution is so important in physics, because any system of state, any physical system in thermodynamic equilibrium can be described like this. Like you use this in solid state physics when you're looking at the distributions of holes and electrons in the semiconductor material. Okay, and then fine. So that this is the distribution. Now, as you change T, what happens is that you get different solutions. If T is very small, if T is small, implies that if T is small, then what will happen is probability of X is concentrated near peak of P of X, okay? If P is large, then it's like P of X equals a constant. It's uniformly distributed over all the states. Oh. Okay. So here's what's kind of interesting. And I guess I'm completely out of time. But what happens is that the Ising model was kind of a breakthrough, because what it turns out is that there's a critical temperature. Beta C is critical temperature. Okay, and this physically occurs in real materials. In fact, I don't know if anybody, they used to have things called optomagnetic drives or optical drives. I mean, they were used them in like Next computers. I don't think anybody has them anymore, but does anybody remember them? I might have one of the old drives around. You could buy it. So the way it worked is that it had a laser. It was like a CD, okay, but it was in a case, so it looked more like a floppy drive. Of course, nobody knows what floppy drives look like either. But and then the floppy drive, what would happen is that a laser would fire on the spot and heat it up and raise it above the critical temperature, okay? And when it was above the critical temperature, it would magnetize spontaneously according to the ambient magnetic field. And then when it cooled off, then it would retain that magnetic polarization, all right? So you could record information on a disk like that. So you have a disk like this, and it's spinning around, and the laser fires that point. So this is a laser. I don't know what a laser looks like. Let's say it looks like that. And then there would be like a magnetic coil here. And the magnetic coil would create an ambient magnetic field. So it would record the magnetic field polarization at the time that the laser fired on the disk surface. And they had a special material in there, which was a magnetic, thin magnetic layer, kind of approximates a 2D, a field of like an Ising model. And here's the thing that makes it cool, that this has a very interesting property that at least one guy won a Nobel Prize for this, back when the Nobel Prize meant something, okay? And what happened was that And what happened is that you can show that above the critical temperature, you get long scale correlation. Above the critical temperature, you get long scale correlations in the grain structure associated with these magnetic field grain boundaries, okay? And below the critical temperature, you get long scale dependencies, and above, you don't, okay? So, and the critical temperature, you can actually measure, you can mathematically calculate, right? And so this is beta, inverse temperature here. So this is a really interesting, it was the first time they were actually able to they mathematically model the physical behavior they had observed in this nonlinear behavior in this material properties, okay, of the Ising model. And the reason it is because of the loopy dependencies. In a 1D case, you don't get this kind of phenomena, right? Because you don't have any, so it's sort of like, you might think of it as the feedback loop. You know, if I tell somebody something and they tell me, we sort of self-reinforce until we come to a full agreement, and then we're not going to change our minds, okay? It kind of reminds you of some stuff that goes on recently. But anyway, in this case, okay, when you have this kind of thing happening, now what can happen is you wait long enough, eventually the chain, no matter what state you start off in, the chain eventually becomes ergodic, okay? But here that's not true. And here, if you have the boundary of this being all ones, then no matter how big this thing gets, you can get infinitely far away, and still in the center of this thing, it's going to be mostly ones because of this loopy dependency that creates this critical temperature phenomena, which is exactly the physical material property that people observed before they had a mathematical model to describe it. And it's kind of interesting, the history of this. I read about it a little bit when I was writing this section, that this guy Ising originally proposed all this, but Ising himself never knew what he was doing, I don't think. And the guy who actually proved all this was this guy named Onsager. Where's Onsager's name? I just saw it. Okay, there's a guy named Onsager who proved all this. And I even have a little proof about the existence of the critical temperature in here. Where's Onsager's name? I just saw it. Oh my gosh, I'm losing my mind. Onsager. Oh, here it is. Amazingly, in 1944, Onsager was able to obtain closed form expressions for the properties of the Ising model as n goes to infinity. That truly is unbelievable, because this is before, I mean, they weren't doing this on computers. The first computer was in like 1947, 48, and that was the ENIAC at the University of Pennsylvania, which, by the way, when I was an undergraduate at Penn, I used to have to walk on the ENIAC to get in and out of the labs because they had it lying on the floor. So that was kind of interesting. Now I think they have it in a museum. But yeah, so interesting. Yeah. So so that's pretty much that. Let me see. Stop sharing. So at this point, I guess I'll stop recording. So bye.